Hello and welcome to another episode of 5-Minute Paper Series. I'm your host, Osmel Martinez, and today I'm going to present you one of our most recent publications titled Minimization of the Worst Case Average Energy Consumption in UAV-Assisted IoT Networks. So why UAVs? So I will put some examples to see whether when we can use a UAV, when they are more suitable. First is for emergency scenarios. You see that this case, setting up a base station, a traditional base station will take a while sending an UAV will be much more faster to collect some information. The next one, it's regarding collecting some measurements, let's say from a field. In this case, setting up an entire infrastructure of traditional base stations will be costly, and the UAVs can offer a more flexible solution. So whenever you change the layout of the network, the UAV can fit easily into this. And the last one is extending the coverage. So this is a different way of doing relaying. You see that the sensors is outside the coverage area of the cellular network. So to use the same services, one thing you can use is to use an UAV as a relay. So this is the system layout. We are using an UAV that serves a set of IoT nodes that are deployed to the area, and they can be in active and inactive states. So our goal in this paper is to minimize the worst case average energy consumption. We have four main constraints. The first one is regarding the recovering, the success of the recovering algorithm at the UAV. So we have set up a target S INR. Here we're using a grant-free random access protocol. The success of the recovering depends on these parameters. You have some power restrictions. It can be either to power limitation, spectrum regulation. We have some aviation regulations, and because we're using also a configurable antenna, we have some beamwidth constraints. So the optimization algorithm split the original problem, which is non-convex and highly nonlinear, into three GP problems. And the idea is to solve the problem in different, each problem solve a different number of variables. For instance, the first problem takes as an input to the position of the UAV, and then it outputs the height, the power location, and the beam width of the antenna, while the second one takes the height and the beam width of the antenna and solve the 2D position of the UAV, the power location, and some parameter T that we will use for measuring convergence. Whenever this convergence is achieved, we can jump to the final step. This is a finite tune of for computing the power allocation. If not, we return back to the other step. You see that the most costly steps, which are the first two problems, scales linearly in terms of iterations, while in terms of arithmetic operations, the scaling is exponentially. Regarding the numerical analysis, we will analyze the two different scenarios. One is a deterministic or cellular-like deployment, and the other one is a random deployment. We have two benchmark methods. One is iteratively method, and the other one is genetic algorithm. And these are intended for solving the original problem without any transformation. So the impact on the target is INR. The main picture here is that, of course, as you tie the SINR constraints, the average SINR will increase, but more importantly, increasing the number of devices benefits, show some marginal benefits when you plan the network. And although in the right side, you see that the GA shows solve the lower height for the UAV, together with the iteratively method doesn't show, they don't show good results when you plot it against the objective function against the SINR target. That's why I don't show this. Here's an example of the impact of the number of devices. Consider that you have CR2032 battery, and the lifetime we're measuring is with respect to the iteratively methods battery transfer chain IoT devices. So just by using GA, we have a gain of 27 hours while using our algorithm. Give us a gain of 1,574 hours additionally. So and you see that this gap keeps increasing. With respect to the average processing time, these results, with respect to the algorithm one, you see that this matches with the previous result. So this is a linear increase, while the others are showing an exponential increase with respect to the number of devices. So here we have the impact of the coverage area, and we are using, in addition to the reconfigurable antennas in our scenario, we're using a scenario where the UAV has a traditional antenna that cannot control the beamwidth. And you see that as I increase this beamwidth, the objective gets higher, while using reconfigurable antennas gives better results. Even though the height, as you see in the right, is lower for using fixed antennas. So that the main point here, the optimal strategy is fly higher and keep the beamwidth as small as possible. That's a flexibility that the UAV gets by using reconfigurable antennas. So in this paper, we propose an algorithm for controlling the devices power allocation, UAV position, and antenna configuration. We have some marginal benefits of planning the network, especially in dense deployments, and the worst case average energy requirements increases as the UAV flies higher to serve wider areas. So that agrees with the previous results that we just showed. So for more information about this publication, you can visit the IEEE Internet of Things journal. The paper is published there, and it's also openly available in ResearchGate and archive. So that's all. Thanks for your attention, and see you in the next episode of 5 Minutes Paper Series.